Get record. All right. So today will be a little longer than like last week's classes because I'm doing 8.1 and 8.2. Whenever we have a week that we have office hours, it's always a little bit longer the next time. But um, 8.1 and 8.2 lays a nice groundwork for chapter 9 and chapter 10, which chapter 9 and chapter 10 are a lot of meat, but they don't, once you get the concepts of 8.1 and 8.2, chapter 9 and 10 are not quite as difficult. Hopefully, I'm hoping it is not too scary for anyone. We're going to be okay. It's going to be fine. We're almost in the home stretch. We're in the end of week 7. It's crazy, just crazy. All right. So I did get all of the feedback done for the final projects. I've been communicating with a few of you, tossing ideas back and forth and everything. So if you haven't read that feedback yet, make sure you read that feedback. So today, 8.1, we're going to talk about distribution of sample means and looking at normal populations, and we have like 2 slides of non-normal populations. And then we're going to look at sampling distribution of sample proportions, and we're going to compute some probabilities with the sample proportions. So you're not getting you will not get any new calculator functions, but you will get new formulas. But we're going to use the same old calculator functions. We're just going to look at some new formulas and start looking at some they're like tests to determine whether or not things are normal and whether or not things are independent and stuff. So we're gonna be doing that. Some of that might carry over into chapter 9. So that's what we're doing today. It's going to be great. You're going to do fine. And so this first part is me kind of explaining what sampling distributions of sample means are. So it's not stuff that you're going to have to repeat to me. So I'm going to just kind of explain it to you. All right, maybe if I can actually get my screen to go to the next screen. There we go. So a sampling distribution is, so we take sample sizes. So for example, let's say that I was taking samples of RCC students. Let's say that I took sample of 20 RCC students. And if I continued taking samples, so if I have a whole lot of samples and I take every single sample of size 20 and I find the mean of every single sample of size 20, that would be my sampling distribution. I'd have to take every single sample of size 20. That is what a sampling distribution is. And I'm going to find the mean of each of those. So that's what the sampling distribution of sample mean is. So, okay, no problem. So, and I'll explain this a little bit better in a minute, but basically, so as we've noticed previously, the sample mean is going to be a little bit different than the population mean. It depends on which individuals are in the sample. So if I take every sample that I can of size 20 from a population, and then I take the mean of each of those samples, it's going to be give me a pretty good idea of what the actual mean is. So obviously, if I'm doing this, I don't know what the actual mean is, but I'm going to be able to use all of the means of all of these samples to get a pretty good idea of what the actual mean is. And that's kind of what we're going to be doing today. So I'm going to give you an example right here. So suppose that the government wants to figure out the average income of all of the households in the US. I can't survey every single household to get the population mean. So they're going to take a simple random sample of 250,000 households, and they're going to find the average income of those households. So I got this average income right here. We've got 72,641. Then I'm going to take a second random sample of 250,000 households, and the average of those is right there. Then I'm going to take another one, and it is right there. So notice that they're all a little bit different, but they're they're pretty close to each other. They're kind of similar to each other. So if I took all of those samples and found the average of all of those samples, so I take all the means, then I find the average of all of the means. I'm going to get pretty darn close to the population mean. So I'm finding the mean of the means. That's essentially what I'm doing. And that's going to give me my sampling distribution and kind of help me to estimate what that population mean might be. So I'm going to show you some diagrams and things, and we'll narrow it down even a little bit more here. So this is the process. I'm not going to be asking you to give me this process back. I just kind of want to give you an idea of how we do this. So you're going to, whatever sample size you decide to use, and chapter in chapter 10, we're going to get a little more specific about what sample sizes you need. And so you can get a good sample size. So just right now, don't worry about what the sample size is. You just take a certain sample. Then you're going to compute the mean of that sample. You'll get X bar of that sample. And so if we have a finite population, I'm going to take another sample and do the same thing, and then take another sample until all of the random samples have been obtained. So once we have one sample, you can't take the same sample again. Obviously, some of the same individuals will be in the samples, but the samples themselves will not be identical. Kind of like if I take a sample of 3 things, there's not. So if I have a sample of size, if there's only a 3 in my population and I want to take a sample size of 2, this is like really small thing. I can take this sample. Then I can take this sample, which is different. It contains one of the same ones. And then I can take a third sample, which would contain this one and this one. So it's contains one of the same, but it's not exactly the same. So there are 3 different samples that I can take of size 2. That's essentially what's happening here. Well, that's not the right thing. I want to delete that. Okay. All right. Hopefully, as we go, this will make a little more sense if it doesn't already. And so you're just taking all of the possible samples and finding the means of those samples. And then what we're going to be doing with this is we're going to be finding the average of all of those means. So we're going to do an example with some pennies. So the weight of pennies minted after 1982 are approximately normally distributed. This is important. With a mean of 2.46 grams and a standard deviation of 0.02. So we're going to approximate the sampling distribution of sample means. We're going to take 200 simple random samples of n equals 5. So I would say that the number of pennies minted after 1982, I wouldn't really call it a finite population, even though technically it's not infinite, but I'd say that the number of pennies that there are is big enough that we're not going to really be able to take every single sample of size 200. So we're just going to take or every single one of sample 5. Think about how many samples that would be. So we're just going to take 200 random samples. That's a lot of samples, and it's going to be big enough that it's going to serve our purpose here. So I took 200 different samples of size 5. Then what I'm going to do is so here's an example. So I took 5 pennies. This is one of my samples. And I took all of the weights of those pennies and I averaged them. So of my sample, this right here is the sample mean of just one of them. But I'm going to do 200 of those. 200 samples of size 5 and find the means. It's going to look like this. Don't worry, we don't have to put it in any calculators or anything. That would take a really long time. But this is the average weight of each of the samples of size 5. So each one of these is an average weight of the pennies, of the 5 pennies. So 200 averages right there. All right. So now what I did was I took all of those sample means, because all of these are different, but the thing with it being the averages of all of those samples is it's bringing me closer to the actual average. They're less spread out. So I averaged all of those. So of the averages, the standard deviation of those means is 0.0086. So this is smaller than the standard deviation of the population because if I'm averaging them all out, my spread is going to be a lot less. If it's the averages, my spread is not going to be a whole lot. Therefore, I have a super small standard deviation. So let me show you what this looks like. So this looks like it's spread out, but take a look here. Look at the bottom to the top, my lowest value to my highest, 2.435 to 2.485, only 0.05 apart from the bottom of this to the top. That is really small. It is 5/100ths apart. Super, super close. So if we were to put this on a bigger scale, they're not that spread apart. The average of my averages it's not very far apart. Therefore, the standard deviation is very small because they're not that spread out. This is one of the reasons we do this is so that our data is not so spread apart, and it's a lot easier to estimate the population mean. Okay, so let's take a look at what happens when we change our sample size. I want to see what happens to the standard deviation when we change our sample size. So I'm going to show you it, and this right here is the truth, and this is what you want to remember. As my sample size increases, the standard deviation is going to get smaller. So as the sample size increases, the standard deviation decreases. So if I'm taking larger samples, so I've been taking samples of size 5, if I took samples of size 10 or size 20 or size 100, my standard deviation is going to get really small because if I'm taking a bigger chunk of all of the data, my average is going to be closer to the population. Like, for example, if I had a class of 30 students and I'm doing sample sizes of 3, I could very easily just choose the 3, like if I'm doing like, let's say weight, I could have the 3 smallest kids in my sample. But let's say I take a sample size of 8, I'm more likely to get a wider variety of students, a better representation of the whole class. So getting a bigger sample size, my standard deviation is going to be smaller. It's going to be less spread out. It's going to be closer. Each one of them is going to be closer to the actual mean. So let's take a look at sample size 20. Let's see what happens. So this is my population, by the way. Population standard deviation is 0.02. And my population, well, that's my population mean is 2.46. So let's see how close we can get to our actual standard deviation, our actual population mean. Okay. So we want a small standard deviation. Small standard deviation means it's not as spread out. So here, sample size 20, I have my mean of my means is 2.46, which is the same as the population. But now my standard deviation is this. Look how much smaller that is. That is like almost half of what it was for 5. So my data is even less spread out. So take a look at here. I'm 2.45, 2.475. This is even closer. It is even less spread out because I now have the sample size of 20. So if I went even bigger, if I went to 100, my standard deviation is going to get even smaller if I was sampling 100. Any questions so far? Are we doing okay? All right. Okay, so because we are dealing with the mean of the means, and we noticed that the sample size, so the sample size made a difference in our standard deviation. we have to be able to calculate our standard deviation using that sample size. This right here is the formula that we're going to use. So we take the population standard deviation, if we have it, it's all samples. Yeah, we're not using the population mean or the standard deviation. No, we are looking at what the mean of all of those means is, the mean of our sampling distribution, right? So we are assuming we know it, or we have an estimate, or we think we know what the population standard deviation is. We take the population standard deviation and divide it by the square root of our sample size. This is going to give us the standard error. So this right here is called standard error. Or sometimes they'll just call it standard deviation of the sampling distribution. They'll call it this right here. Sometimes. When I'm answering your questions in the, like if you send me a message and I'm answering your questions, I will frequently refer to it as the new standard deviation. I will frequently say use the new standard deviation for sample means. So I will frequently just kind of refer to it as that because sometimes we forget what standard error is. So this,
Okay, that's what I was going to ask. So the standard error is the same thing as the standard deviation of the sampling distribution and the new standard deviation. Okay.
I just call it the new standard deviation because for some reason that gets people to understand what I'm going for sometimes a little better than standard error. I don't know why. It just over the years it's clicked. So this is specifically for use with means when we're using sampling distribution of sample means. And this will give us the standard deviation for our sampling distribution. So this is when we are using the mean of the means. And this is the symbol. It is sigma sub x bar. That's what we would call it. Sigma sub x bar. All right, moving forward. Okay, so what we were looking at here, when we had a populate or a stand, when we had sample sizes of 5, calculating it here, I get, using the calculations, I get 0.0089. This is what we found. This was the actual. That was the actual, actually finding all the standard deviation of the data. So it's not exact, but it is 3/10,000ths off. Not a big deal being 3/10,000ths off. But look, when I had this sample size of 20, 0.0045, it is exactly what we found, what the actual was. So when you get the larger sample sizes, it is a little bit more accurate, but it's still close enough when you have a sample size of like 5 because we can't always, it takes a lot. It would be a lot of work to do all of this calculation. So just using the formula is a beautiful thing.
Where did the 0.02 come from?
This is the population standard deviation. That's sigma.
Okay.
They they gave that to us back here. Where is it? They gave it to us back here. They gave us the population.
Okay, that makes more sense.
So in your homework for 8.1, they're going to give you the population standard deviation. Um, Eventually, as we move, once we get into chapter 9, we're not going to have population standard deviation, and I'll tell you how to deal with it then. But for now, they're going to give you the population standard deviation. We're kind of baby stepping our way towards the bigger topics. So this is just foundational. Second here.
Okay, I just like to label the formulas. So I always have arrows that say like this is population standard deviation, this is the sample size, and this is the standard error or new. So, okay.
Perfect. All right.
And the N is the sample size, right?
I will label. And then, so little n is almost always sample size. And then this is population standard deviation. Little n is almost always sample size. Capital N is your population size. So little n is sample size. We're going to deal with the population size in a minute. All right. So we already did that. All right. So if a random variable is normally distributed, the distribution of the sample mean is normally distributed. You're going to need to know this. FYI, you need to know this. I believe your next quiz will ask a question about this. So you need to know this, and then you're going to need to know about when it's not normal. So 1 second, and I will explain what to do when it's not normal. Maybe not 1 second. It might be a little bit longer than that. But if the variable is normally distributed, like the weights of pennies, the weights of pennies was normally distributed. Therefore, my sampling distribution is also normally distributed, which is nice. It's lovely because otherwise, most of the math we do, if we don't have a normal population or what we're working with isn't normal, we can't do much with it. So it being normal is good. All right. So here's an example. We're gonna play with this a little bit. The IQ is a measure of intelligence. We know this. The scores on the test are normally distributed with a mean of 100 and a standard deviation of 15. So we're going to find the mean and the standard deviation of when a sample size of 9. So important. My mu sub x bar always equals the mu. The mean sub x bar equals your population mean. So it's going to ask you in your homework what mu sub x bar is. Whatever that population mean is, that's your mean. My sigma sub x bar, on the other hand, we're going to use sigma divided by the square root of n. So we have 15 divided by the square root of 9. I love that they gave me beautiful numbers that I can calculate in my head. So that's 15 divided by 3. So my standard deviation, my new standard deviation, or my standard error, is 5. All right. Questions before we move on? All right.
Will it be like when you go back? I'm sorry, I'm late to this question.
Oh,
So 15, is it always gonna be things? Can it be a decimal? Is that
Oh, yeah.
okay?
Yeah.
Okay.
Most of the time you're going to get a decimal. They're not always going to give you pretty numbers.
Okay.
Like probably the only time you're going to see pretty numbers on this in ever. So it will be decimals. The mu sub x bar it's the mean of all the means. So it is so when I took all of those averages of each sample of pennies, then I averaged the averages. That is what mu sub x bar is. This is the average of all of the averages, but it's always going to be the same as the population mean. So notice when we went back when we were doing, let me just bump back there. So the population average is 2.46, but my average of my samples was also 2.46. And so then when I went back here for sample of 5, here also my sample mean was also 2.46. So your mu sub x is always going to be the same thing as the population mean. Okay, where am I? There we go. So this will always be true. Mu sub x bar is always going to equal the mean. That's a really ugly mu. All of my mu's are ugly though. No, it's okay. No problem, Kate. I totally get it. I am a mom and grandma. So, oh man, I didn't realize everything was scrolling so slow. Okay, I'm going to give it a second to catch up. My internet, sometimes it is fantastic. Other times it just decides it just wants to be slow. Okay, I get back there. All right, there we go. All right, moving on. Okay, so, so now we are going to math with it. And thank goodness, when we math with it, we're just going to use normal CDF because normal CDF is so easy to deal with. Binomial probability distribution should be in your pocket and don't take it back out unless you're going to use it for your final project. After you take this test 2 in this class, you never have to do binomial probability distributions again unless you want to, or unless you want to use them for your final project. We're not going back to those. But normal CDF sticks around. It still hangs out with us. So the way
Is
to,
all of 8.1 and 8, so is that gonna be the normal CDF?
um not we are gonna be getting some new calculator functions after this.
Okay.
But I'm letting you know that we still will be using normal CDF here, but binomial stuff is going away.
Okay, so for the distribution of the sample mean, normal CDF.
Yes.
Okay.
Okay. So, but there's going to be a twist, and so just wait for the twist. And
Okay.
it's not difficult. It's not a difficult twist. Just a
Okay.
big twist. Okay. So the weight of the pennies minute after 1982 are approximately normally distributed with a mean of 2.46 and a standard deviation of 0.02. So I'm going to take a simple random sample of 10 pennies minted after 1982. So what is the probability? What is the probability that my mu sub x bar is going to be greater than or equal to 2.465? Or just my x bar, actually, not my mu sub x bar. My x bar, the mean of that sample, what is the probability that it is greater than or equal to 2.465? Okay, and I'm going to jump into a homework question at the end of this that throws a lot of people off. So, because this is really important. If it is pulling a sample and I want to know the probability that the mean of the sample is something, I have to use the new standard deviation. So hold on here. So highlight. It says sample. So this word right here tells me use new standard deviation. So that right there is telling me to use the new standard deviation. So I need to calculate that first. My mu sub x bar is going to be whatever mu is. My new standard deviation is going to be the sigma over square root of n. So it's going to be 0.02 divided by the square root of 10. Let me put that in my calculator. I'm going to show you though, because it's really cool. You can actually do math right in normal CDF, and I recommend doing that. So this is approximately 0.006. All right. So what we're going to do is I'm going to do normal CDF, and we're going to do lower, upper, mu sub x bar, and then sigma sub x bar. That's what we are using. Because this is a sample, we're wanting to know something about the sample, I want to know what's the probability the sample mean is greater than 2.465. I need to look at the sampling distribution. So
In my calculator, I'm trying to calculate it. So would you do 0.02 per
divide by,
parentheses? Because I did divided by
so it should just,
10.
okay, hold on here. So 0.02 divided by, where's my divided by? Square root
Oh, square. Okay,
10, like this.
that makes more sense.
Square root is second x squared on your calculator, and that'll give you but take a look here. So I'm going to go to we're going to go to normal CDF, and it's greater than or equal to, so my lower bound is 2.465. My upper bound is going to be 1E99 because it's greater than or equal to, or it's at least. All right. The mean, we go the population mean, which is 2.46. And this is the beauty of this calculator. I can just put the math in here. 0.02 divided by square root of 10. You're more than welcome to calculate it ahead of time and put that number in there. But the reason I like this is because I don't have to do any rounding or figure out where do I round to. I just put it in there and it does the math for me. It's just so beautiful. I hit enter and then hit enter. Bam. So my probability that, rewrite this, give me a second. The probability that, I know you can't see it yet. I'm going to write it because I don't want to lose it off my screen, the number, because I forget stuff. 0.2146. All right. So my probability that the mean of the 10 pennies is greater than 2.465 is about 21.46%. Questions? So see, the only little twist is basically this right here. That's really the only twist, is that we're using the new standard deviation in the normal CDF rather than the population one. I just love this stuff. It just makes me really happy. And I know I'm weird. It's okay. I'm used to it. Okay. So this is just basically what's happening here. And except for some reason, I'm not really sure why, they like to use Z-scores for some reason, even though in the calculator they didn't. But when they're doing it, obviously you can use the Z table, but I don't even care about the Z table. Don't use the Z table. Don't use it. Just use your calculator. And then this just shows you like with the mean. So this is the population mean, and it's just showing you what's happening. Okay. So we're going to do this again. I would like you to try this, and I'm going to work quietly behind you. So the IQ of humans is approximately normally distributed with a mean of 100 and a standard deviation of 15. Compute the probability that a simple random sample of size n equals 10 results in a sample mean greater than 110. So this is what we're looking for. So go ahead and work on it. I'm going to work quietly behind you. I'm going to let you get started and then work quietly behind you. What I'm putting in my calculator. What did we do? So my question is, would it be unusual to have a sample size of 10, have an average IQ of 110 or more? Would that be considered unusual? It absolutely would, because that probability is less than 5%. So it would absolutely be unusual if I took a random sample of 10 people and averaged their IQs together. Questions? Wasn't too bad, right? Didn't scare anyone yet? Notice I said yet. No, it's still, none of it's bad. None of it's bad. It's not terrible. Okay, I'm gonna move on. Okay. So now we're going to talk about if we don't have a normal population. So for example, right here, the relative frequency of rolling a dice. So they all have the same probability. This is not normal. This is symmetric, but not normal. This is a uniform distribution. But my average, my mean is 3.5 and the standard deviation is 1.708, but this is not a normal population. This is not complicated either. You get one slide right here. So I'm going to show you, actually, there's a few slides, but let me show you what happens. So the first thing I'm going to do is I'm going to take 200 simple random samples of size 4. And then I'm going to do it with size 10, and then I'm going to do it with size 30, and you'll see what happens. So here's with size 4. So if I take samples of size 4, this is not quite normal. I mean, it's getting there. It's pretty close. It looks like it's slightly skewed to the right, but it isn't terrible. But take a look. Now I got size 10. This is starting to look pretty good. This one almost looks like it's skewed to the left. Look what happens when I get size 30. This is a nice, beautiful, normal curve. Nice, beautiful bell curve. So as our sample sizes get bigger, a non-normal population will become, the sampling distribution will become normal. Generally, the rule of thumb is sample size of 30 or larger. So if we have a population that isn't normal, or we don't know the population is normal, taking a sample size of 30 or larger will make the sampling distribution normal. And then we can do all our math stuff with it. I think my next slide says it. Yes. This is called the central limit theorem. And when you answer your question on your quiz, it's going to ask you about what makes it normal. This right here is important right here. And then this right here, greater than n, greater than or equal to 30 is recommended. Well, that doesn't spell recommended. So if you have a sample size of greater than or equal to 30, it doesn't matter if your population is normal or not. Then your sampling distribution will be normal. And I don't care if you remember it's the central limit theorem, and it's not a bad idea to remember that, but just remember that if you have the larger sample size, a non-normal population will become normal. And 30 is a great number to remember if you can put that in your head. So that question's on the quiz, because the quiz frequently has like vocabulary questions and conceptual questions and things. And so I believe that that's on the quiz. See, benefit of watching these videos and or coming to class is you get all of the nitty gritty about what's going to be on the quiz.
So the sample mean just basically is all the means added up. It's
all,
not
it's the average.
the mean of the means.
Yeah, so the sampling distribution of sample means is the mean of all the means. Yes.
Okay.
It's a lot of words, I know.
No, it's okay. I was just reading it. So when it says the shape of the distribution of the sample mean, it means that the means have already been memed.
Yes.
Memed. Okay, so okay.
So basically what we did was we took all of these samples and we found the means, and that is our new data set. All of those means is our data set. That's what's normal. That's what's here. This is the data. This is all of the means of the samples of size 30 put into a histogram. That help?
Yes, it really did. Sorry, I just missed that in my notes, and now thank you.
Perfect. It's good. It's because we say the word mean so many times, it kind of loses its meaning. And it's kind of like once I say a word too many times, I'm like, does that even word even mean what I think it means? All right. Okay. So we're gonna do a problem or two, and then before we get to the 8.2, I do want to jump to my open math real quick on 8.1 and show you something, and then we'll come back. All right. So suppose that the mean time for an oil change at 10-minute oil change joint is 11.4 with a standard deviation of 3.2. If a random sample of 35 oil changes is selected, describe the sampling distribution of sample mean. What all this means is tell me mu sub x bar and sigma sub x bar. That's all it means by describe. They're using big words for something super basic. So the mu sub x bar is always going to be the same as the population mean. Our standard deviation of sigma sub x bar divided by the square root of 35. And it's not going to be pretty. They're always just going to be a decimal, or almost always. I got approximately 0.54. I guess I could put 0. Yeah, I could put 0.9. Why not? So it's about 54.1%-ish. Okay. So now what this wants to know, if a random sample of n equals 35 is selected, what is the probability the average oil change time is less than 11 minutes? We already did one of these, but it's good to have more practice. Yeah. So less than 11 minutes. So it's negative 1e99, 11. Uh-oh. Mu sub x bar, which I guess I should put the number in there, comma, 3.2 divided by the square root of 35. This is what I will put in my calculator. Do this along with me. Hopefully you get a nice, pretty number. Oh, it's an ugly number, but how'd we do? Did we get the same thing?
I think I already asked this, and this should be, I guess, by now common knowledge. So if it's in the lower, you do the negative 1e99, and if it's in the upper, you just do 1e99.
Yes, because
Aaron, have barbecue chicken.
a negative 1e99
Same, we got the same.
infinity, and 1e99 is positive infinity. So
Okay.
negative infinity, and then positive is positive infinity.
Okay, because I accidentally wrote E99 one of the times on the upper, and it gave me the same answer. So I just started getting confused.
So we have about almost about a 23% chance of having an average of an oil change of less than 11 minutes if we took a sample size of 35. All
If
right.
you were to draw that on a bell-shaped curve and that new standard deviation that's 0.54, what would that look like? Standard deviation on the chart would still, there would be 3.2 minutes between each section.
Because once we take a whole lot of samples of size 35, our data set is now those means. It's those means of the samples. So I still have the 11.4 here, but now I have 11.4 minus 0.54 there. So now it's like we've swapped because our new population is the means of the samples.
Okay, so it means that the standard deviation would be about half of one.
On this one, yes.
Yeah, yeah,
Okay,
okay.
so I'm gonna this it might help when I jump to my open math because we're actually gonna see a distribution on a curve. So that was actually really good timing. So let me go to 8.1. There's a couple of questions I want to look at. We're gonna do that one first. So this one right here. This is a question I get the most questions about. So this curve, this diagram here shows the sampling distribution. So if you look at this, the mean is 140 and the sigma sub x bar. So the new standard deviation is 2 because you can see it goes up 2 here, goes down 2 here, goes up 4 here, down 4 there. But I don't have the population standard deviation. But I do have a sample size. I'm gonna see if I can. I'm trying to find a good spot to do math on my iPad. So I have, let's see here, n equals 25. I'm looking for sigma. And then I have sigma sub x bar. So when you look at this, when you get to this question, you're going to be like, I don't have enough information to find the population standard deviation. Realize sigma sub x bar is in this diagram. So my sigma sub x bar is 2. You have to get it out of the diagram. So I'm going to go back to my iPad. So I wrote the information right here. It wants me to find sigma. So basically what I'm doing is I'm using this formula and I'm plugging in what I have and I'm going to solve for the other one. So I have sigma sub x bar. I don't have sigma, but I do have the sample size. So this is what I'm doing. You're just going to solve for that. Just use your algebra skills and solve for sigma. Just going to math it out. So it might ask you for the sample size. It might ask you, or it might ask you for sigma, depending on which one you get. You're either going to have to find the population standard deviation or find n. If you were finding n, I'm going to pick a random number. Actually, let's just see what this is. So, okay. So if it told me that my population standard deviation was 10 and I wanted to find n, I would do this and then I would solve for n. So depending on what you're solving for, just use this formula and then solve for it. Okay, let me show you the other question that people have problems with. This one right here. So this one has population is normally distributed. It gives you the mean and the standard deviation, and it gives you a sample size. All right. So right here, this one right here, find the probability a single randomly selected value is less than 215. I'm looking for a probability of X. This one, you use the original standard deviation, the 3.3 with your normal CDF. This one right here, now I'm finding the probability that the sample size has a mean less than 215. This one, you're going to use the new standard deviation in your normal CDF. So notice the difference. This one is a single randomly selected value. This one has a sample size, and I'm looking for the probability that the mean is less than 215. So regular standard deviation, new standard deviation. Those are the two questions people ask me about the most. So I figured I would pop in. All right. Now, we are done with 8.1. So if you keep track of that sort of thing, we are now moving on to 8.2. Put the mean stuff in your pocket. We're not going to use that anymore. The stuff that we just did with the sampling distribution of sample means, put that in your pocket. We're going to look at a different kind of sampling distribution. All right. So we've done a point estimate before. We've called it other things. Point estimate is if I took a sample and I figured out what proportion of the sample has a specific characteristic, I would take the number of successes and divide them by the total number of trials or the sample size. It's kind of like relative frequency. It's the same thing as finding the proportion of something. So how many yellow M&Ms are there in a whole bag of M&Ms? What proportion of those? It is the same thing. When we have a sample proportion, when we take a sample and we figure out how many in that sample have a characteristic, it's called p hat. Whenever anything is an estimate, we just put a hat on it. I don't know why, but we just call this p hat. A sample proportion is p hat. It's also called point estimate, and I can't tell you a really good reason why, but it is also called point estimate. Point estimate is, there you go. And sample proportion and point estimate, same thing, p hat. Okay, so in this section, we're doing basically the same thing that we did with the sample means, but this time what we're doing is we're taking a whole bunch of samples, and in each one of them, we're finding the point estimate. So for example, let's say that I had 100 bags of those mini M&Ms, and in each mini M&M bag, there are 20 M&Ms. So those are my samples, the 20 M&Ms in each of those sample bags. I would find out the proportion of M&Ms that are yellow in each one. So then I would have all of these bags of M&Ms, and I'd have the proportion of yellow M&Ms for each of those samples. So I'd have tons of sample proportions. That's what we're doing here. All right. So a Quinnipiac poll conducted in May 2008. We took 1,745 registered voters and asked them whether they approved of the way George W. Bush was handling the economy. 349 said yes. So we're going to get a point estimate. So my p hat is going to be 349 over 1,745. I'm going to put that in my calculator so I can get the proportion. But my calculator needs to be turned on. So this is approximately 0.2. Actually, it's exactly 0.2. So it's 0.2. So about 20% of the people in that particular poll felt that George W. Bush was handling the economy well. That's it. But for every single sample, if I took 500 samples of size 1745, each of them would have their own p hat. Okay, I'm going to move on. So we're going to do it again. 1,000 adults, ask them if they were on currently on some form of low carb diet. 150 out of those 1,000 said yes. So my p hat be the 150 divided by 1,000. I know this is very familiar because we've done this a few times before. So 15%, I don't know why I put that in my calculator. So about 15% of the ones polled were on a low carb diet. All right. Okay. So once again, we're going to do the same kind of experiment here, where we're going to take a look at what happens as sample size changes. Okay. So 42% of registered voters believe, in 2008, believe that gay and lesbian couples should be allowed to marry. This is the population proportion. I'm going to write that there. Population proportion. That wasn't a poll, that was a population proportion. Now what I'm going to do is I'm going to take different sample sizes and we're going to see what happens. I'm going to create some histograms. Okay, here's the first one. This is a sample size 10. You can see it's kind of skewed right. My mean is 0.426 and my standard deviation was 0.160. My population mean was 42%. Pretty darn close. All right, Let's move on. Let's do it again. Now I take these sample proportions. Look at how bunched up in the middle it is. So now we're at 0.426 still, my mean is. Standard deviation now is at 0.072, very small number. It's all bunched up in the middle. Let's get to the last one, sample size 100. This is pretty much a normal curve. Look how small my standard deviation is. And take a look at my mean. It is now the same as the population proportion, which is the cool thing because normally with proportions, we would have to use binomial probability distribution. And you know what? Most of you weren't big fans of binomial probability distribution. So the cool thing with using sampling distributions of sample proportions is because we have all of these samples that we're taking the proportions of, we now can average all of those samples together and we can use normal CDF now. We can get a standard deviation out of it. We can get a mean out of it, and we can just use normal CDF. We don't have to be fancy. However, the new standard deviation or standard error is kind of fancy. You can still put it in and have the normal CDF do the math for you. So let's take a look. So this is important though. As the size of the sample increases, the shape of the sampling distribution becomes approximately normal. So once again, you are going to have a question of this on your quiz. Give me in a couple of slides. I'm going to give you a little piece that I want you to mention. Okay. So this center right here, the mean of the sampling distribution of the sample proportions is equal to the population proportion. So here's what I'm saying. My mu sub p hat is equal to p. So my mean of all of my samples is equal to the population proportion. The standard deviation decreases as the sample size increases. It's the same as with the means. As the sample size gets larger, my standard deviation is going to get smaller. Makes sense. We've already kind of discussed why this happens, and you saw it with the histograms. Everything was squishing closer. Okay. But you're going to be asked about this, but there's one more piece we're going to add to it in a minute. All right. Here we are. This is the piece we're going to add to it. Right here. So what this is saying is that as long as I have a large enough sample size, my sampling distribution is going to be normal. What this is saying is this, I have to have, because the reason you need larger sample sizes is because I need to have enough successes and failures to get an idea of what the population looks like. So this right here, this little formula, if you use this, then it will tell you whether or not your sample size is large enough for the sampling distribution to be normal. That's what that's going to tell you. So with it 42%, let me see here. So our 42%, so when I did 0.42, what was my sample? So my first sample size was just 5, wasn't it? Let me see, hold on a second here. My first sample size, oh, it was size 10. So let's take a look. I can't get back. So times 10. I did this backwards, it's okay. 1 minus P, so 1 minus 0.42, 0.58. Let's see if that gives me a large enough sample size. 0.42 times 0.58 times 10. This is only 3.57. That sample size was not large enough for me to have for me to say that that is normal. Because this is too small, I can't say it's normal. I can't use all of our tools that we're having. But if this, let's change it. What was the other one? 20. Let's change the sample size to 20, which is just going to be double that. So now it's at 7.14. Still not okay. So now I'm going to change it to 100.
And what you're trying to get it larger than 10?
I want it bigger than 10. So I'm
Okay.
trying to find a sample size that will get me larger than 10. So we noticed back here, this was not normal. At 10, it wasn't normal. At 20, oh, I didn't do 50. I did 20. I didn't even try 50. Let's try 50. 50 looks pretty normal. I think 50 is going to be good. So let's do 50. Oh, that's a pencil. Okay, well, here I am. I think 50 is going to be good. Yeah, so this right here is 12.18. So that's good. 50 was a good sample size. 50 allowed us to have a normal shape so that we can move forward and use our analysis methods. So so that's what we need to check. So on your quiz, you can state that that the distribution becomes approximately normal as the sample size gets larger. But I would love it if you say as long as that right there, as long as NP times 1 minus P is greater than or equal to 10. Because that right there is your test right there.
So the sample mean needs to be 30 or greater and the sample size of
Okay, so our samples, when we put our sample size into this right here, as our sample, we're not using 30 in this. It's only with the means. Put that in your pocket, the 30. This is for the sample means, 30 was our rule of thumb. For the sample proportions, for the sampling distribution of the proportions, we use this instead of 30.
Okay, that's what I'm writing. Sample proportion. Thank you.
You're welcome. So when we're using proportions, this is our tool right here. This is NP times 1 minus P is greater than or equal to 10. And that will be able to tell you, yes, now my sampling distribution is approximately normal, so I can use my analysis methods. Okay. So we also have a new standard deviation for this, and this is what it looks like right here. So we take the square root of the population proportion times 1 minus the population proportion and divide it by n, by the sample size. This is our new standard deviation for population proportions, or sampling distributions of p hat, of sampling proportions. That's what I meant to say. This is the formula that we use for this. And it's used the same way. It is used exactly the same way that we used the last one. So we're going to do some examples. We really are almost done. We have 10 slides left, and you know how I have a lot of like useless stuff on slides. So we're almost done. Y'all are doing amazing. Okay, I'm going to move it on. Okay, there's other things that are required here. Okay, you need a little cheat sheet. I believe I have one. Hold on. I'm pretty sure. Hold on a second here. I mean, look where you guys can actually see things. Where are we? We're in week 7. Okay. I believe that there's something in here. Let's see here, chapter 8. Yeah, right here. So right here, if you click on this, take a look. It's all right there. It breaks it up for you. Once you print this though, and you're probably going to want to write this, hold on a second here. So important things. We need to determine that things are independent. So in order for this, it requires independence for these sampling proportions. So our sample size can't be too big. If our sample size is too big, when we take lots of samples, we're going to have way too many of the same individuals in the sample. So we need to make sure that our sample size is no more than 5% of the population. This is where that capital N comes in. So our little n needs to be less than or equal to 5% of the entire population. So that is one rule that we have. So I think, I'm not sure if 8.2 asks you this or not, but when it says something like verify the conditions have been met, this is one of the conditions. These are the two conditions you are verifying, this condition and this condition. So if it says to verify conditions have been met, I'm going to write these words down. If it says verify conditions have been met, these are the conditions. These are the conditions. So if it asks you to verify the conditions have been met, those are the two things that you're verifying. The sample size is no more than 5% of the population, and NP times 1 minus P is greater than or equal to 10. At that point, we can use this. Even though it says regardless of whether or not, we still kind of just use it. And I mean, we get an idea, but we can use that, and we can do all of our analysis methods that are coming up in the future. Chapter 9 and chapter 10 are some super useful things that we're going to be doing. And so these conditions need to be met in order to do that. If they're not met, you can state, even though our sample size doesn't satisfy NP times 1 minus P is greater than or equal to 10, I'm doing this. So you still basically still do the math with it. You just have to give it that caveat by saying, you know, that this doesn't fit that, but I'm going to use this anyway. So that way people will kind of take it with a grain of salt and be like, okay, this might not be completely accurate, but at least it kind of gives me something to go on, if that makes sense. Kind of like a covering yourself type of a thing. All right, so let's move on and do some math. So in June 2008, Time conducted a poll. 42%, we already kind of saw this one, 42% of registered voters believe that gay and lesbian couples should be allowed to marry. Suppose we obtain a simple random sample of 50 voters and determine which voters believe that they should be allowed to marry. We're going to describe the sampling distribution. Once again, when you describe the sampling distribution, all you are doing is verify the conditions have been met, and then verify the conditions have been met, and then find the mean and the standard deviation. So first things first, my sample size is less than or equal to 5% of the population. That's all that means right there. I'm saying 50 is less than 5% of the whole population. Good. That has been met. Good job. NP times 1 minus P is greater than or equal to 10. So I have my N is 50, P 0.42. This is N, this is P. 1 minus P. So we're going to math this out.
Are you just using common sense to say that 50 is less than 5%?
Yeah. Yes. I mean, obviously, because you think about how many registered voters there are in the US, 50 is definitely less than 5% of all the voters. Usually there's going to be no doubt. Okay. So this equals 12.18, which is greater than or equal to 10. So we're good there also. There was one problem. So I was teaching AP Stats at the high school for a while, and there was one problem that they gave us, that the sample size was clearly more than 5% of the population of the high school. And it was really annoying because I didn't even want to do the math, but it was the problem in our curriculum, and I just had to do it. And I wrote a little note on it saying, not less than 5%, but we're doing the math anyway. So, but any problems you get, it's going to be pretty obvious it's less than 5%. So now we're going to say our mu sub p hat equals 0.42. Because remember, I'm going to write it up here, mu sub p hat equals p. And this is p. That was easy. Now, standard deviation. Our sigma sub p hat equals square root of p, so 0.42, times 1 minus p, which is 0.58, divided by 50, which is our sample size. You could put this whole thing in your calculator, but if you put the whole thing in your calculator, put parentheses around your whole numerator. Otherwise, you're going to get bad stuff happening. So give the numerator its own parentheses. I'm going to just show you. I'll go to my calculator. Okay. So I'm going to do square root of, I'll do 0.42 times 0.58, close those parentheses, divided by 50. So make sure the numerator gets its own parentheses. So I have approximately 0.0698. So that's my sample, that's my new standard deviation. Okay, this is all you have to do to describe this is how you describe your sampling distribution. Put these 4 things. So if you get a question that says to just describe the sampling distribution, these are the 4 things I want. Questions so far?
Yeah, I'm sorry. I was writing and doing math and didn't hear you. Where does the 0.58 come from?
That's 1 minus 0.42.
Oh, okay.
I can tell you every single time, and I don't even know why I write 0.58, because every single time I do that, someone's like, where did that come from? It's okay. It's on me. I know better. It's totally on me, especially since doing math at 6:45 on a Thursday evening. You probably have had a long week and probably don't have the best. So did you put your, and see, that's way too big. Did you put your
12.18 is to show that it's larger than 10.
oh yeah. Okay. Okay. I was confused. I was looking at that going, something's wrong here. Are you good? You're good, Courtney? Okay. No problem. We're good. I know you people on the video are like, just listening and watching this later are like, I don't know what's going on. It's because all the fun stuff happens in the chat. You guys miss out on all the fun in the chat. All right. And my cat is attacking my arm again. Okay, we're going to move on. Look at that. They just did exactly what I did. Because I have found, um, I have found that people tend to retain things better if I'm doing the math and talking through it rather than giving you this wall of words here. This is really good for if you printed off the PowerPoint and just want to see it nice typed pretty. But I have just found walking through it seems to help people better than just giving you this wall of words and numbers. Okay, we're going to move on. We're going to do one on our own, another one, because it's a good idea to do that. All right. So we have 6 slides left. Based on a study conducted by good. I'm glad, Kate. I'm glad that helps you. Based on a study by Gallup, 70% of Americans, 76% of Americans believe that the state of moral values in the United States is getting worse. This is an old poll. I wonder what it is today. I think it'd be higher than 76. I don't know though. That would be a really great final project question. Anyway, I don't know how it would work for a final project really, but it'd just be fun to find out. Suppose we obtain a random sample of n equals 60 to determine which believe that the state of moral values in the United States is getting worse. We're going to describe the sampling distribution. I would like you to work through this, and I'm going to work through it quietly behind you. So I would like you. You want yogurt hut with gummy sharks? Ooh, that sounds good. Let's all just go. Let's just go get gummy yogurt hut with gummy sharks. Just ditch the math. That sounds like fun. All right. See what you did there? I am going to do the math behind you. Do There's not a whole lot of math because it's just the description. See if you can remember the 4 things on your own and try to get this done. If you get stuck, go ahead and look up. I want to do that last. Ooh. A new Monster energy drink that tastes like gummy sharks. Oh my goodness. Okay. Y'all distracting me with the cool stuff that's happening in the chat. Okay.
I think I'm confused with the larger than 10, but no more than 5%. Like,
Okay. What this is saying right here, what this says right here is that sample size less than 5% of the population.
okay, I got that one. I think it's the larger than 10, the sampling distribution to see if your sample proportion is large enough. So,
This is saying that these are like large enough sample. Enough sample.
so couldn't you just look at the 60 and say it's larger than 10?
No, the 60 doesn't need to be larger than 10. The 60 times p times 1 minus p needs to be greater than or equal. Because if my p was like 12%, I might not get larger than 10. So if you have a really small proportion, you might not get there. Or so you just need to make sure that your sample size is greater than or equal to 10. You just need to show that. And 60 probably is good enough, but you've got to show that. But notice that he's barely good enough, right? If I would have done 55, I might not have gotten there because this is 10.94. And this is just the way we do things. So,
Okay.
so you need to show these 2 things, and then we have these right here.
Okay. Yeah, the mu and the standard deviation, those 2 I'm set on. I don't know. It's just gonna take some practice with the other ones too.
And this is just conditions we go through. And so, especially if you go on to Math 244 later on, I don't know if any of you are going to 244, but if you go to 244, all of this stuff becomes more important because this is like the intro class. 244 gets a little bit more into the meat. And then if anybody is super crazy like me and decides to major in math, once you do the 361s, which are the higher level things, all of this becomes super important. So right now, this is just kind of like, here's an intro and these things need to happen. But if it doesn't, just indicate it. But it gets super intense when you get to the higher level things. But this is an intro class, so you get kind of little bits and pieces of a lot of things. All right, we're going to move on. We're going to actually do some math now. We are on slide 41. Look at us. Look at us go. Uh-oh. And then I just shut off my iPad. There we go. Okay. So according to the Centers for Disease Control and Prevention, 18.8% of school children aged 6 to 11 were overweight in 2004. In a random sample of 90 school-aged children, what is the probability at least 19 are overweight? Yes, this is an intro class. Yes, it is. Okay, so we're looking for the probability that the p hat of that sample is greater than or equal to 0.19. This is what we're looking for. Okay. I'm not going to do all of the testing things. I think that you probably could, if we were going to do that, I'm sure you could be able to say that 90 is going to be less than 5% of the entire population of school-age children. I think we all can agree with that. And trust me, NP times 1 minus P is greater than or equal to 10. We're not going to go there. We're just going to jump straight to using the mean and the standard deviation. I'm going to move it down because there's not enough room. And my mu sub P hat is going to be 0.188. My standard deviation sub P hat is going to be square root of 0.188 times 1 minus 0.188 divided by 90. This is going to be approximately something. Let me math this out.
Is your mu always a rounded to 3 decimals? Because you took it.
No, well, I just take whatever's there. That one gave me 8.8, so I used the whole 18.8. If it was 42%, 42. So it's just whatever they give me. Okay, divided by 90. So I have my standard deviation 0.0412. I guess I'll go that far. Okay. So once again, I'm going to put the formula for the standard deviation in my normal CDF, but so I'm going to write it like this. So once again, it's going to be normal CDF, and it's going to be lower, upper, mu sub p hat, and then, and then go back to the screen apparently, sigma sub p hat. Because we're asking that 90 school, this is the nice thing about this, is that we don't have to use binomial probabilities because we're using a sampling distribution, so it's so nice that we can kind of set binomial probability stuff aside. So let's go to my calculator. All right, we're going to do normal CDF, so second vars down to normal CDF. So we want to know the probability it's greater than 0.19. So my lower value is going to be 0.19. My upper is 1E99. Our mu is 0.188. My standard deviation, I'm going to put the formula in there. Second, and I'm going to do 0.188. There's going to be a lot of parentheses here. Times 1 minus 0.188. Close my parentheses. Close my parentheses. Divided by 90. Close that last parenthesis. So I have 1, 2, 3 opened. Now I have 1, 2, 3 closed. Put the math right in there, hit enter. Hit enter. So we've got approximately 0.48, so about 48% chance that the proportion of kids in that sample that are overweight is at least 19. That's what that's saying, because this is what is the probability that at least 19% are overweight. So at least 19% of the 90 are overweight is 48% chance. So about a 50-50 chance. So now what this is asking me, I'm gonna kind of hold on a second. I'm gonna make this a little bit smaller. I need a little more room. Okay. So I took a random sample of 90 kids. What if I took a random sample of 90 kids and 24 of those kids were overweight? So what I need to do here, basically what we're trying to figure out is when they ask a question like this, the what might you conclude? First thing I need to figure out is this unusual? That's pretty much what this question is asking. So if I took a sample of 90 school-age children, and 24 of them were overweight, I need to figure out if this is unusual. So I'm going to find my p hat here. My p hat, oh, that is not a pen, that's a highlighter. My p hat is going to be 24 out of 90, which is 24 divided by 90 is 0.266. There's a couple of different things you can do here. And you choose which one you like better, okay? So one thing you can do here is you can determine the z-score of this number right here. You can determine that z-score. So what I can do is I could do 0.266 minus 0.188, because this is my mean, divided by 0.0412, which this is my standard deviation. If I take that z-score, I'm going to be able to determine if this is unusual. This is one way to do this. This is kind of my preferred method. What is that? Did I put the right number in there? 0.266, 0.188. Do I have this on the next screen? I do. Okay. Equals 1.89. It's not unusual, but it's still kind of high. It's almost to the unusual point. The other way that you can do this, and I think this is the way that our curriculum kind of wants it to be, is I could do normal CDF and say, what is the probability of getting 26 or, see, getting that or higher? Given that we have this information. What would that probability be? This is the other way to do that. Z-score is unusual if it's higher than 2. I know it's been a while since we've looked at these. So remember, with a z-score greater than 2, it's unusual. But if I do with normal CDF, I can put, I'm just going to do it. I'm going to move over to the next screen. Once again, put the math in here. So I want to know, I'm going to put in 24 divided by 90 right in there. I already have the rest of it. So what's the probability it's that or greater? It's, oh, how come I didn't get an unusual z-score? Did I do something weird? I don't know what I did, because this is 0.28. I must have done something wrong. Hold on. Okay, let me see here. So 24 divided by 90 minus 0.188. divided by 0.0402 I got a different answer that time. So see, this shows unusual because this is less than 5%. So I don't know what I did wrong. Let's see what this says right here. What did it do here? In a random sample of 90 school, okay, so it says at least 19% are overweight. All right, let's go to the next screen. Okay. What did I do? Okay, we did that right. 1 second here. This is all
The 0.19.
okay. That was the other problem. So this right here, the 19%, that's the other problem. That the first problem we did. Got the four.
Okay.
Okay. So what I'm trying to look at is this right here. So that they did the oh, okay, that's the problem. I did the Z score. It did the probability I got a Z score greater than 1.91. So it's 0.028. Okay. So this ends up being less than 5%. So because it's less than 5%, it would be unusual. So what we do is we talk about why is it unusual? When it's the what would you conclude? If it ends up being unusual, we determine what would we conclude. I usually make up a story. I would conclude that maybe we ended up with more kids out of areas that are food deserts, or maybe we just happen to have a large number of students that, I don't know, had poor eating habits, whatever. You can make up a story, or you can just say, maybe our actual population proportion isn't 19%. Maybe it is something different. So I usually I'm not going to get mad at you for any kind of a conclusion you make. Don't worry. I am not going to get mad at you. As long as you tell me it's unusual, I will say, okay, it's unusual. I just usually make up a story. So I think we've got one more example.
So now I'm confused though. Can we go back to that just for a second? So
Huh?
if you said if the Z score is less than 2, it's not unusual.
And
So I'm confused.
the
Because you said the Z score has to be above 2.
and I'm trying to figure out. And I believe that, let me see here. Give me 1 second. 1.911 E99. Because it gave me, and I think it's because generally we're looking at having tails. And I don't know, it has more to do with empirical rule as opposed to actual numbers, because the empirical rule is estimates, because had our +2 standard deviations and our -2 standard deviations. And it has to do, their estimates, because it's not exactly 2. It is close to 2. And that's kind of why we use the 2 standard deviations as a rule of thumb. The number is actually closer to about 1.9-ish. But if you would have done it with a Z score and said that it's really close to unusual or whatever, I would totally accept it. You're probably going to have values that are going to be extremely unusual. I think the next one's like that. So I would, as long as your math is good, I'm not going to split hairs. As long as your math is good, we're not going to split hairs. So whichever method you use, if you got the 1.91 Z score and you said it's not quite unusual, but it's really close, and maybe we should take another sample, I'm going to call it good. So
Thank you.
yeah. So don't fret about that. I believe this one is like more far away. So we're going to do this one more time, and actually this is our last slide, so we're doing awesome. And look at that, we just barely after 7. All right. So a random sample of 120 Americans. So what we have here, 15% of all Americans have hearing trouble. So we're going to take a sample, random sample of 120 Americans and find the probability that at most means less than or equal to. So at most 12% have hearing trouble. So what we're looking for is the probability that the p hat of our sample is less than or equal to 0.12. That's what we're looking for. So I'm going to go down below because I don't really need more room. So my mean, remember that your mean is equal to the population proportion that we're given. Okay. My standard deviation is going to be the square root of 0.12, 1 minus 0.12, divided by my sample size.
Can I ask a quick question before you keep going? Wouldn't your mean be 15% or is it
Oh,
just
I don't know
12%?
where I got the 12%. Thank you.
Okay.
The 12% is a number that's somewhere in my brain. Oh, it's because that's this. My brain got stuck on the sample. Thank you. I got stuck on the sample. All right, thank you. What would I do without you? All right, so I got approximately 0.0326. So now we're going to use our normal CDF. Just put it right here. And it's at most, so it's negative 1E99. And then 0.12. 0.15 and 0.0326. You don't have to put the math into your normal CDF. You absolutely can just use the 0.0326. I'm just a bit of a perfectionist. Whenever possible, I can get away with not using rounded numbers. I don't. So you don't have to do that. You can just type that number in there. My upper is 0.12. Something weird. What did I do? I did something wrong. Okay, there we go. Did you get 0.1787? We get this number? Yes, okay, good. Yay, all right. So now we're going to suppose that we got a sample of 120 Americans who regularly listen to music using headphones. 26 have hearing troubles. So my p hat is 26 out of 120. That's my p hat. So we want to know what the probability is of getting 26 or more that have hearing trouble. So you can put into your calculator normal CDF 0.12, 1E99, 0.15, 0.0326. And I'm going to, after we do this, I'm going to explain to you how you know if you're doing more or less. So after we do this, oh, this is not 0.12. See, I didn't even have to have anybody check me. Whatever 26 out of 120 is, I would just type it in there. I'm going to give you, afterwards, I'm going to give you how you know whether to put it as more or less. So if you're asking that in your head, I will tell you in a minute. So I got 0.02 about. So since it is a 2% chance, it is unusual. So this one, the story that I would talk about is the fact that they took Americans who regularly listen to headphones. Because this is an unusual value, I'm thinking that possibly this is evidence that headphones could cause hearing loss. I might take a new sample of 120 Americans that regularly listen to headphones to see if this is consistent or if maybe this was just an unusual sample. So the way that we decide if you're going greater than or less than when you check if it's unusual or not, the way that we decide is, so this p hat right here, this p hat right here is approximately 21.2167. Uh-oh. Because that number is significantly larger than the 0.15 that of the population proportion, I'm saying, what's the probability of getting that or higher? I need to go the part of the curve that doesn't include the population proportion. So for example, I'm going to draw my curve. There's my curve. So my 15% is right here. So this one is 21.67%. So it's over here somewhere. So my normal CDF is going to be shading the area that doesn't include my mean. You go for it. This is the last slide anyway. Go to Yogurt Hut. So if I would have had a p hat, let's say that I had a p hat that had only, what if it was like 8 out of 120 was my p hat. So 8 divided by 120. So that would be 0.067. That would be landing me way over here, right? So 6.7%. Therefore, in this case, I would be shading over here. You're shading away from the mean. The area that doesn't include the mean is where you're shading. So that one would be less than or equal to. Does that make sense? Was that helpful? Do I have one more slide? Oh, nope, it's just blank. It just like creates an extra slide and it makes me think I'm not done. That was it. That was the extent of this lesson. And I know it was kind of long. Y'all are such troopers. But go Yogurt Hut. All right. While we're still recording, any questions for the recorded session? I'm gonna turn off the recording. If I can find it.